All right, so this is one of our homework problems. First thing we need to do is find the reactions. So I'm going to draw a free body diagram of the structure. And like I've done previously, I'm going to assume positive shear. I'll call that point A. And positive shear, I'll call that point B. So I'll come back here and label this A and B. And then I'm going to come over here and I'm going to replace my my uniformly distributed load with a concentrated equivalent. And what should be the value of that concentrated equivalent? The area under the curve, right? So 1.5 times 1, that's pretty easy. 1.5 kilonewtons. And let's see, from A, what's the distance? Yeah, it's 2 meters and then half a meter. So 2.5 meters. So with that, this should be pretty easy to find the reactions. With this setup, I'll first some moments about point A, set it equal to 0. So this concentrated equivalent force creates what kind of moment about A? Positive or negative? Negative. So I've got 1.5 kilonewtons times its moment arm of 2.5 meters. And then the positive shear at B also creates negative moment. And it has a moment arm of 3 meters. You guys probably have to help me out. What's the shear at B? Looks like it's going to be negative. 1.25. 1.25? Is that what it is?
Yes.
So that's a 1.25 kilonewtons. It's negative. And then we can come over here and sum our forces in the y direction. That shouldn't be too hard to do. So I have the shear at A acting up, minus the shear at B acting down, minus our concentrated equivalent force of 1.5 kilonewtons. So what should be the shear at B? 0.25, right? That seem reasonable?
Yeah.
That doesn't seem too bad. Okay, so a little statics to get started. Now I'm going to come back over to my original diagram, and I'm going to quickly draw a template, which will kind of give me an edge. Another place that's probably something's going to happen is right here where we have this transition from no load to some load. So at about 2 meters over, I'll add another line to my template. And then from that, we'll establish positive X and positive shear, and all of our units will be in kilonewtons. Okay, so what is the shear at A? 0.25 positive. So we're going to start here at 0.25. Now we know that the change in shear between any 2 points is the area under the load diagram, right? So what is the area under the load diagram over the first 2 meters? 0. So there's no change in shear. So that means my shear should remain 0.25. We also know that the slope of the shear diagram is equal to the load. And what's the load over the first 2 meters? 0. So 0 slope gives me a line. It looks like that. So constant shear. Now, what's the change in shear from 2 to 3 meters? What's the area under the load curve? What is the area under the load curve? Yeah, base times height, 1 times 1.5, and that's acting down, so it's negative. So 0.25 minus 1.5 gives me negative 1.25, which is great because we knew that our shear at B was negative 1.25. Great. Now, what is the slope of the shear diagram? It's equal to the load. And the load is constant. So constant slope, and it's negative. So there's my constant slope line, and it's negative. In fact, if you actually marked it, you would see it would be negative 1.5 to 1. So there's my shear diagram. Now, there's a point here where we go from positive shear to negative shear. That point's going to be interesting to us. Why? What happens when the shear is 0? It indicates that the moment will be maximum or minimum. So that's a point of interest. So I'm going to add that point to my template. We'll go back and find that in a second. I'll go ahead and define my positive x-axis, my positive shear, and my units will be kilonewton meters. Now, so I'm going to call that distance, say, x1. How can I find x1?
Linear equation.
That's one way to do it. I like to use these. So what I'm going to do is I'm going to project that value back up, x1. And remember, the change in shear is the area in the load curve. So what's the change in shear from here to x1? What is numerically the change in shear? It starts off at 0.25 and drops to 0. So that's a change in shear of negative 0.25 kilonewtons. Right? What is the area under the load curve over that same position? Well, it's this area. And what is that area? Yeah, it's base times height. Base is x1, height is 1.5. So I get 1.5 x1. And these two things are equal. Oh, by the way, that's acting down, so that's negative. So that means that if I combine these, I get 1.5 x1 should be equal to negative 0.25. And you can solve for x1. What is it? What's 0.25 divided by 1.5? It's going to be pretty small. Okay, I didn't hear you. I'm sorry. 0.167. 0.167, and that'll be meters. Okay? So now we're ready to move on to the moment diagram. Now, do I know the moment anywhere on my structure? What's the moment at A? 0. That's a good thing to know. 0. What's the moment at B? 0. So I know where I'm starting and I know where I'm going. I'm also going to have to zoom out a little bit here. I know that the change in moment between any 2 points is the area under the shear diagram. So I'm going to go from here to here, 2 meters. What's the area under my shear diagram over those first 2 meters? It's a positive area. 0.25 times 2 is 0.5, right? So that means I'm going to go to 0.5. So this will be 0.5. I also know that the slope of the moment diagram is the shear. What's the value of the shear here? Constant and positive. So here's my constant positive slope. In fact, if you marked it, you should see 0.25 to 1 up. Now, what's the change in moment over this next little small piece here, this 0.167 meters? Well, the change in moment's the area of the shear diagram. That's this little triangle right here. The area of that triangle is 1/2 the base, which is x1, times the height, which is 0.25. How much is that? How much? So it's be 1/2 the base, which is 0.167 meters, times the height, which is 0.25 kilonewtons. So what's all that turn out to be? 0.02. Anybody else get that? 0.02. Exactly? Okay, that's close enough then. And it is positive, so you're going to add that to 0.5, so that should get you to 0.52. Okay, so the slope is the shear. The shear starts off positive and drops to 0. So at that point right there, I should have 0 slope. So it's a little bit of, I may not have it directly, but it's a little bit of a curve, and it flattens out at the top. Now the change in moment is the area under the shear diagram. So now I have this area, right? That's a negative area. And again, it's 1/2 base times height. The height here is 1 point. So this will be 1/2 the base. Well, this was 1 meter, and we found x1 was this. So that means it's 0.833.
Yes.
Yep. And then the height is minus 1.25. Hopefully that will be negative 0.52.
It is.
Yeah.
So that brings us back to 0. Now what's the slope? Well, the slope is given by the shear. The shear starts off at 0 and ends up what? A large negative value. So I'll just kind of sketch in a large negative value, which just happens to be 1 to minus 1.25. And then I'll try to draw a line that fits into that. So 0 slope going down. Looks something like that. So there's my there's my moment diagram. So what's the maximum moment in this structure? Yeah, so the maximum moment is equal to 0.52 kilonewton meters. And where does it occur? From A, looks like 2.167 meters. From A, at this point right here. So now you know the value and the location. So any questions about that? Anybody get that, by the way? Yeah? Cool. Did you get it? Did you get it, Mr. Kettler? I'm sure you were working on that when you were doing Mas Fina Cerveza.
See.